Okay, this is a video recording of Lesson 7 titled Object-Oriented Wrap-Up. And to be clear, this is a wrap-up of our discussion of object-oriented programming in this course, but obviously it's not a comprehensive conclusion about everything there is to know about object-oriented programming. So there are courses out there that are like that are specifically for learning all the different aspects and concepts and techniques of object-oriented programming, but this is not that course. And furthermore, I mean, so much is learned about object-oriented programming by practice. So as you practice trying to write object-oriented programs, you are going to develop your own opinions and techniques and patterns you like to kind of go back to write object-oriented code. So just keep in mind that nothing about this is comprehensive. This is just kind of where we'll stop talking about it in this course so we can move on to some other ideas. Okay, so there's this diagram. It hasn't changed much, and this is where we left off. So this is what we talked about in Lesson 6. We talked about these 4 object-oriented principles of abstraction, polymorphism, inheritance, and encapsulation. For abstraction, we talked about how a user can interact with a car using the abstraction of a steering wheel and 2 pedals, and that's all they have to understand in order to use the core functionality of the car. So we talked about abstraction in that sense, and we also talked about encapsulation, where the user also doesn't have to think about all the complexities of a car when they use it. So 2 closely related ideas there, abstraction and encapsulation. We talked about polymorphism, for example, electric, hybrid, and gas cars all have very different underlying components and details to how they work, but because they share the same abstraction of a steering wheel and 2 pedals, they can be used interchangeably. And then inheritance, we talked about in the Hogwarts example, where there's students and professors at Hogwarts, and they have a lot of things in common: first name, last name, favorite jelly bean, and we could put all those commonalities in a wizard class, and then the student and the professor can inherit from the wizard class, and that's a way that they can you can share common features of objects in code. Okay, so you would think maybe if as long as we learn all these 4 object-oriented principles, you know, if we master these 4 principles, then we'll know everything there is to know about object-oriented programming, and that just is not the case. So what I did is I Googled, you know, what are the object-oriented principles, and the first search result is actually not this acronym what I just showed you. It's these other things here. So other people claim that the 5 main principles follow this acronym SOLID. So single responsibility principle, open-close principle, Liskov substitution principle, interface segregation principle, and dependency inversion principle, right? So whatever those are, right? So here's a whole nother acronym that's coming up, and here's our acronym below, the 4 we talked about. And there's all these different ways that people render the ideas that are behind object-oriented programming. So you know, these 4 pillars are not exhaustive by any means. So I'll pull up that other acronym here. So the SOLID principles, we're not going to talk about these except for this first one. Okay, so the single responsibility principle is pretty much exactly as it sounds, and that is the single responsibility principle says that every class, module, or function in a program should have exactly one responsibility or purpose. And I couldn't have said it better myself, so I've quoted these words. But even more useful to how I like to think about it is that every class should have exactly one reason to be changed. So if there's any guarantee in your software, it's that it will need to be changed. So the requirements of the software are going to change over time. The business logic in your software will need to be changed over time. The properties you have on your classes and your objects will need to change as requirements evolve or as the software evolves. So change is bound to happen, and the sign that you have really strong software design, really strong object-oriented design, is that when a new requirement comes to your software, or maybe a change in an existing requirement comes or needs to be made into your software, there is one class that you can kind of pinpoint to and isolate and say, well, if we change this class, then the new requirement will be met by the software. So sometimes that's wishful thinking, but generally that's the goal. New requirement needs to be made, or a requirement needs to be modified. You find the class that's responsible for that element of the software, and you change that class, and the change reflects throughout the whole system. Let's talk about this with an example. So if we think back to lesson 5, we made this bank account class, and the bank account class had 2 withdrawal methods, one for withdrawing money with less than 500 in the withdrawal request, and the other one was for withdrawing money with more than $500 in the withdrawal request. So if you needed less than 500, you would call this withdrawal method. If you needed more than 500, you would call this withdrawal method, passing in a Social Security number to confirm that the Social Security number matched the one we had on file. So we had 2 withdrawal methods, and we called both of them like this. So in our program class, we checked how much the user was asking for, and then we called each withdrawal method accordingly, right? And when we called this one, we had to do this extra step of getting a Social Security number to confirm. Okay, so and here's the internal withdrawal method here. So both of these withdrawal methods call the internal withdrawal method here, and this is what actually performs the logic of taking money out of the account and giving it back to the user, and it also performs or also handles the bank's overdraft policy. Okay, so that's all encoded in here in this internal withdrawal method. So student asked a really good question in class, and that's why did we not just do this? Why didn't we just make our program class simple, right? So how much you want to withdraw, okay, we get that number, and then we do account.withdraw. And when we call in the method for account.withdraw, if we happen to be passed in an amount greater than 500, then now in the bank account class, we get the Social Security number to confirm and perform this confirmation. So if we did this, because in this way we have 3 different methods. We have withdraw taking in a Social Security number, and then we have internal withdraw, so that we're not duplicating code between these 2 methods. But with this way, now you just have one method, and you're just handling that contingency in this method in the bank account class. And so the reason we didn't do it this way comes back to that single responsibility principle. So the single responsibility principle says a class should only have one reason to change. And, as you can expect, if our bank account policy changes, so say our overdraft policy changes, right? So to be a little less, sharkish, right? If our overdraft policy changes, then of course we're going to need to come into the bank account class and update this logic for doing the withdrawal. But now we also have another reason we'd need to change, right? So now say we were using a different user interface. Say we weren't using a console. Say we were using a web application or a desktop application or an ATM for performing the withdrawal, right? If you're using these mediums, now you're going to have to come into this bank account class and update this code to work with your new user interface. So you now have two reasons to need to change this bank account class, and because we want to avoid that, that's why we set it up like this. So while we have the lesson 5 exercise in mind, there's kind of one more little thing I want to mention here. So when the user called the regular withdraw method with greater than 500 in the amount they were seeking to withdraw, we just returned 0, right? They called the wrong method. They were supposed to call this method if they wanted more than 500 that took in the social security number. But they called the wrong one, and we just returned 0. And we could do something a little bit harsher than returning 0, though, and that is throwing an exception. So what we can do is, if you call this withdrawal method with too much money, then you throw a new, in this case, argument out of range exception, right? So think about it like throwing an error. When a software throws an error, we could also think about that as throwing an exception. So, and so argument out of range, so the argument being the amount, and then we provide a message saying the amount must be under 500, right? So when we do this, this means if someone called this, right? So if you were executing this code in Visual Studio, then first off, Visual Studio is going to freeze, and it's going to give you this message, this error message that says you have an unhandled exception. We can't move on because your program has encountered this exception and has not handled it, and so then the program terminates. So I'm sure you've seen this as you've been developing. Maybe you've seen like index out of range exception, object not set to instance of a object, for example. So you've probably seen these while you're developing, and this is how they come into play, right? This is how they come into play. And so another thing to say is that this is a good practice because it signals to someone using your bank account class or who's using your object that they have used it incorrectly. So we're saying, you've used this incorrectly, and I want to let you know that you used it incorrectly. I really want to let you know because whatever code is calling this method needs to understand that it needs to be calling this other method in this situation. So it's kind of a signal to other parts of the program that an object is being misused. Okay. And so I think we'll talk about this again later in the course, but just wanted to mention this here. Now back to a slightly different topic of polymorphism. So we talked about how polymorphism says that objects with the same abstractions can be used interchangeably regardless of their underlying implementation. And we talked about the 3-car example, right? The electric, hybrid, and gas car. They share the same abstraction, so they can be used interchangeably. And another great question that we had in class was why, so how we did this is we made this abstract class car, and then we had the electric car inherit, or the Tesla inherit from car, and the Prius inherit from car, and the Honda Civic inherit from car. And but car was abstract, right? Because we were just defining the common abstraction of a car. That's what we were using the abstract class for. And so the question now was, why is car an abstract class? Why couldn't it be a concrete class? Why couldn't it just be public class car? And so I wanted to kind of get at that with a simpler example. So if you think about bills, right? Phone bills, tuition bills, electric bills, gas bills, any kind of bill, right? Abstractly speaking, all bills have these things here. So public class bill, and they have an account holder name, an address, and a total amount in dollars, and they have some formula for determining how much the bill should cost, right? So we have this abstract idea of a bill, but an actual bill is going to be for something, right? So it's going to be a cell phone bill, it's going to be a tuition bill, and it'll have all those properties, and additionally, it'll have some properties that are relevant to that type of bill. So data used in gigabytes in the case of a cell phone bill, and number of credits enrolled in case of a tuition bill. It's going to have these other properties on top of the base class properties, and it'll have its own implementation for determining how much a bill should cost. And so the reason we don't want to make bill a normal class is because, I guess, intuitively speaking, if you received a bill but you didn't know what it was for, right, that wouldn't be cool, right? Right. Generic bills that aren't related to anything you're actually using, it's not cool. So, and in our example here, Visual Studio is going to tell you it's not cool. Because bill is marked as abstract, that means we cannot create a new bill, right? So that we have a small program that's attempting to create a new bill. The bill class is not meant to be created. It's meant to define the common abstraction of this, that all bills have these things. Okay. Now, of course, the other thing holds true, though, that you can have a list of bills, right? A list of bills, but the new bills you're creating are cell phone bills and tuition bills, and you can use these different types of bills interchangeably for example, determining the cost and how much Alan's bills are going to be total. So that's kind of the answer there, is that the bill is meant to be an abstract notion, and that's why we use abstract, because it's not okay to give bills that aren't for something. Okay, now there's one more language construct that I'll mention here to enable or support polymorphism. And so we saw the abstract base class that you inherit from, but now we have another construct called interface, right? A C# interface. And so for the abstract base class, we go public abstract class bill. But for an interface, it's not, the word class isn't even involved. It's just called public interface and then the name of that interface. And interfaces are helpful when there are objects that share a common abstraction, but they are not nicely related. Okay, so the example I have here, I borrowed this example from somewhere. I don't remember where, but I think it shows that things can have the same interface or common abstraction, but not really be relatable in a way that you can create this inheritance structure to create polymorphism or to enable polymorphism. So interface is the I-annoying interface, and anything that has the anything that implements the I-annoying interface has a method called annoyHuman. Okay. And so we have some things here. So we have a class. This is a class, but the class implements the I-annoying interface, and we have the spam caller. The spam caller implements the I-annoying interface. And because they implement the I-annoying interface, they have to have this annoyHuman method, okay? Because that's what the interface said. The interface said, if something implements the I-annoying interface, it better have a method called annoyHuman. And so these have exactly that. But these things are not really related in any other way other than they can do this, other than they can annoy a human. And the way they annoy humans is so very different that it doesn't make sense to have an abstract base class and then start inheriting things, right? So that's where the interface is particularly helpful. Okay. So and of course, once you have this, then if you have things that implement the iAnnoy interface, right? So you have a list of annoying things, and we don't know anything about the things in the list other than they implement the iAnnoy interface. That's all we know. It doesn't matter what's in that list, what we put in that list. All that matters is that they implemented that interface, so we can add mosquitoes, we can add spam callers, and then we can use those interchangeably in the program. So here's your for each loop that is just looping through and calling that method. So that's kind of an introduction to why you might want to use an interface, and I'll also show a slightly more realistic example here. So here is so when you ask for a credit score, when you're going to take out a loan or apply for a credit card, the person giving the loan wants to check your credit score. And so they are going to run your a credit report through 3 different credit bureaus and then take an average, and then they'll use that as your credit score for determining your risk level in the loaning process, right? So standard banking process here, and we can say that if something is a credit report service, that means they will implement these 3 methods. They'll have some implementation for retrieving a credit report, some implementation for reporting an on-time payment, which would raise someone's credit score, and then some method here for reporting an unpaid debt, right, for lowering someone's credit score. Okay, so this is our common interface, and we can create these different credit report services that implement this interface. So we have Experian, we have Equifax, and we have TransUnion, and the implementations for executing an Experian credit report versus an Equifax credit report, they could be very different, right? And not in a way, and not set up in a way where you can nicely inherit between these things. All right, it could be the case. I'm not exactly sure, but it could be the case. But we can say, the implementation of these credit report services might be very different, but we know at the end of the day that we can get a credit report for them, we can report an on-time payment to them, and we can report an unpaid debt, right? So these are what we know at the end of the day, and we know that because they implement that interface. Okay, so and so there's implementations for all of these. I've just hidden them. Okay, they've been hidden. Okay, so here is an example again, doing what a bank might do when they're preparing a loan, right? That now they can have this program that creates these credit report services and then can calculate the credit score. And so calculating the credit score is a matter of looping through these credit services and executing the credit report and getting the credit score. So and the beauty of the interface here is that this method, calculate credit score, has no idea what the credit report service is, right? It doesn't know if it's Experian, Equifax, or TransUnion, but by using the interface, we can make this algorithm agnostic to that, right? This algorithm is just, I don't actually know how we're getting these credit reports, but assuming we can get the credit report, then we can get the total score and we can perform the averaging and give that to the caller. Okay, so that's kind of an idea of why we like interfaces for doing this. Okay, that's it.